So in this lecture, we're going to see about the Maxwell's stress tensor. Okay. So what we'll do is we'll try to calculate the total force. Okay, the electromagnetic force on the charges in some volume V. So as I said, the formula is the general formula. We write it in integral form now. The general formula will be, let me write it out. So this you would recognize is the general formula. Let me write it down. F is equal to QE. This is the electric field contribution due to the total force, and then we have the V cross V force. Okay, then we have the QV cross V force. QV cross V. Now this I would write. This is what this is. I write it as, I take the Q common, and the Q can be written out as the charge density, volume charge density integrated with respect to the volume. Integrate the entire volume, we'll get the total charge. So that is what we are doing here. And what we can do is, we can, this rho and V, I already said J can be written as rho V, right? Already showed you that derivation. J, how J can be written out as rho V. So we make that substitution and we get this term here, and we take the rho inside, so you get the rho here. Now the charge, the force per unit volume. So here, how do you get the force per unit volume? You divide by the total volume, or you remove the integration with respect to volume, so you get this term. Now we'll have to work on this to so we'll have to evaluate this right expression on the right. Now first, this rho, I'm going to write it out as epsilon times del dot E. This is from Gauss's law, right? Gauss's law says that del dot E is equal to rho by epsilon naught, right? So from that I write out an expression for rho. And then this J, I can write it out as this J, I'll write it out as in terms of this expression here. This is J. This comes from Ampere's law, right? Ampere's law, what does Ampere's law say? Del cross B is equal to mu naught J epsilon naught dE by dt. This is Ampere's law. So you get that from there. You just solve for J and you get substituted here, you'll get it there like that. Now what is time derivative of E cross P? Now this is just the UV rule. I'm just applying the UV rule. Okay, so this is U and this is V. So U prime V plus V U V U prime. Okay, V U prime V, no sorry, U V prime. Oh sorry, I'm getting it wrong again. So this is taken as U and this is taken as V. So U prime V plus U V prime. Okay, so that's right. So we do that, and d by dt can be written out as minus del cross E. This is from Faraday's law. So you can write out del E by del E by del, sorry, d partial derivative of E with respect to time cross product D has this expression. Okay, you can write it out as this expression. Now so when you substitute that here into, so when you multiply this out, you will get here. So we're just multiplying it out. Okay, we're just multiplying this expression out here, this expression for F. Let me see if I can show the cursor here. So we're multiplying this expression out and we substitute what value we got here. Okay, when we do that, we get this expression now. Okay, and we add a term del dot B multiplied by B because we simply in our formula we'll be using, it will be easier for us to write a simplified formula. So for symmetry purpose we add it, but it contributes nothing, okay, because del dot b is 0, right? So it contributes nothing, that's why we add it, and it is useful for us in writing out a simplified formula, that's why we're adding it. And this is a product rule, okay, this is a product rule in vector calculus. Del square of a vector square, okay, sorry, del gradient of a vector square, okay, can be written out this way, okay. So now you just get an expression for this one, e cross del cross e. You get an expression here because we have e cross del cross e here, that's why we're writing it out like this. So we substitute it here, okay. Similarly we have b cross del cross b, and that also can be written out in a similar way. So when we do all that, you essentially get this formula. Now you would recognize that this will be the energy term, right? We'll come to that, and this will be the Poynting vector term, e cross b. So we'll come to that in a moment, but we can write this entire expression 8.16 in a simplified way if we introduce the Maxwell stress tensor, okay. So using the Maxwell, this is the Maxwell stress tensor. Now I and j are just indices. Now when I and j are equal to each other, what will happen? You know that when the Kronecker delta function, how it works is, when I and j are equal to each other, it becomes 1, right? When I and j are not equal to each other, it becomes 0. Okay, so this term will become 1, that is e square will appear in the expression when I and j are same, okay, and here also it's the same. So b square will appear when I and j are the same. When I and j are not the same, it won't appear. So this entire f expression for f now can be written out in terms of this Maxwell stress tensor as in this fashion. F is equal to, f is equal to divergence of t. So this t is the Maxwell stress tensor, okay, and plus minus u naught minus epsilon naught u naught ds by dt, where s is the Poynting vector, okay, s is the Poynting vector, okay. Now this is, so far we've got force per unit volume. So if I want an entire force, we have to integrate both sides with respect to volume, right? With respect to the volume, you have to integrate it. So when you integrate this term with respect to the volume, what you would get is, so integrate using the divergence theorem, we can write it out differently. Del dot t d tau, okay, d can be written out as t dot dA as surface integral. This is a divergence here. So that's what we've done here. And so that's what we've done here. And now we've got the total electromagnetic. So, and we integrate this with respect to volume, take the derivative outside and it integrate with respect to the volume. The rest is the Poynting vector. So this expression here is completely represented by this formula here, okay. This expression here completely represents this expression encircled. So now we've got the total electromagnetic force on charges in V, and the expression 8.20 gives the total electromagnetic force on the charges, so on a collection of charges in a volume V.